Now we'll look at how to solve the Welte mutual funds example we formulated before. Shown here is a problem statement and the linear programming model we formulated. Remember the goal was to maximize the return from these 5 investments. The decision variables were defined as the dollar amounts invested in these 5 places, and the constraints are here. The first constraint said the total amount to be invested is equal to $100,000. The second one said the amounts invested in the oil companies, Atlantic and Pacific Oil, should not exceed $50,000. And the third constraint said the amounts invested in the steel companies, Midwest Steel and Hoover Steel, could not exceed $50,000. The fourth constraint corresponded to the condition that the amount invested in government bonds should be at least 25% of the amount invested in the steel industry. So originally, we wrote the constraint like this: the government bonds greater than or equal to 25% of M plus H, and then we wrote it this way. The last constraint here corresponded to the limit on the Pacific Oil Company, that the amount in Pacific Oil had to be no more than 60% of the amount in the oil industry, and then we ended up rewriting it this way. We will follow the similar steps as in the RMC example. There are some things that are different. Now notice here there's a lot of just summing of the variables. So a lot of coefficients will be 1s in these constraints, like it's be 1a, 1p, 1m, 1h, 1g, and here it'll be 1a plus 1p and then 0, 0, 0 for the other coefficients. Some coefficients are negative, so we should remember to add the negative signs in such cases. Also, there are constraints of different type. We got here equal to, less than equal to, greater than equal to, so we got all 3 kinds of constraints. So we won't be able to enter all the constraints in one row when we go to the solver box. Now we go to Excel. It shows the optimal solution here. Again, for the purpose of demonstration, we'll delete all the values and formulas and then redo it. We have the variable cells here, and we'll enter the coefficients here. So for the objective function, here are the coefficients. So let's put those in. Now the coefficients for the constraints. So remember, this is like 1, 1, 1, 1, 1. And here's 1, 1, and then 0, 0, 0, and here's 1, 1, like that. So here we're going to put 1, 1, 1, 1, 1. Then you got 1, 1, then 1, 1 for the steel companies. And the fourth constraint, we would put negative 0.25 and negative 0.25. And then for G, the coefficient is 1. And the last one, negative 0.6 and positive 0.4 here. Okay, now for the objective function here, for the total return, we would use a sum product function of the coefficients and the variables. Okay. And to make it more interesting, we'll put some numbers in here. It's optional. You could just leave those blank, but I prefer to put some numbers in here so that we could check how the sum product formulas are working. So here I'm just going to put 1, 2, 3, 4, 5. Okay, now for the left-hand side of the constraints, again, sum product function of the coefficients, comma, and then the variables, and don't forget the dollar signs. Close the parentheses. Okay, and then I will just go over here and double click to fill in the rest of the column. Here we put in the inequality signs. First one is equal, second one is less than or equal to, and the third one. Fourth one is greater than or equal to, fifth one is less than or equal to, and on the right hand side we would put these numbers. So we got here 100,000. And 50,000, again 50,000, then 0, and then 0. And the slack, again the slack was right hand side minus the left hand side. Now we go to solver. Again, everything is already filled in, so I'm going to reset all and do it over. So the objective cell here is the total annual return, and you want to maximize it. And the variable cells are over here, 5 cells. The constraints, you want to say add. Now the first constraint is equal to, but the second constraint is less than or equal to, so we can't do them together. So we would just do the first one and then say equal to, and then here click on the 100,000, then say add. But the second and the third constraints are the same type, so at least we could do these two together. And then add the fourth one, then greater than or equal to, and here we click on 0. Then add the last one, less than or equal to, then we click on 0, and OK. So there should be 4 rows of constraints because the second and the third one, we did them together. And now make sure that this part is checked off and the method is selected as simplex LP before you solve. So let's solve. And we have the solution. Now let's summarize the answer over here. So what do we want to do? So you want to invest $20,000 in the Atlantic oil, $30,000 in the Pacific oil, nothing in the Midwest Steel, $40,000 in Huber Steel, and $10,000 in government bonds. So that's the recommendation from the optimal solution. And what will that give us is the $8,000 in return. So total return from this will be $8,000. Now I should point out that you don't really have to use a sum product formula every time. For instance, like this first constraint, here you just have to sum the variables. So I could have done it this way. I could have just said sum, all the variables. And that would have given me the same result. And here, again, I could have said, well, it's just a sum of the 2 variables. So I could have said sum, now these 2 variables, and so forth. And that would have been fine. Now I'm recommending using the sum product formulas for the left-hand sides just because it allows us to have the same structure for each problem. Now you got all the coefficients in this one table, and the left-hand sides of the constraints all have the same sum product formulas. So with this kind of structure, you don't have to think too much. Once you have the linear programming model, you just follow the same steps. Coefficients here, sum product formulas here. Now we'll answer some questions based on the results we just obtained. First question, what is the rate of return from this portfolio? We know that the dollar return is $8,000, and that's out of investing $100,000. So we would say the rate of return is $8,000 divided by $100,000. So 0.08, or in percent, 8%. So that's the answer here, 8%. The second question, suppose Pacific Oil's rate of return is decreased to 8%. Will this change the investment recommendation? And by how much will its rate have to decrease in order to make a difference in the investment amounts? So let's take a look here. Remember that the Pacific Oil had the highest rate of return. Between the Atlantic Oil and Pacific Oil, the only difference was that the Pacific Oil had a higher rate of return, 10.3% compared to 7.3%. But because Pacific Oil was more risky, there was a constraint that said Pacific Oil's amount could be no more than 60%, of the amount invested in the oil companies. And that's why here you could see the total amount in the oil industry is 50,000, and out of that, 30,000 was invested there because that's exactly 60%. Now, to answer the question, what happens if Pacific Oil's rate of return is 8%? All we have to do is change the number here and then run solver again. Again, to keep things organized, I'm going to make a copy of this before I make that change. And here, on the copy, I'm going to make the change to 8% and then run solver. Now, what do you think will happen? If the Pacific Oil's rate of return is lower than before, then maybe we wouldn't invest as much money in the Pacific Oil. But then, is this low enough, 8%? Because 8% is still higher than the rate of Atlantic Oil. So let's see. Now we're going to click on solve, and you could see, well, no, there is no difference. So there's no change in the investment amounts. So that makes sense because the Pacific Oil's rate of return is still higher than Atlantic Oil. And of course, you could see that the total return has changed because the return we get from Pacific Oil is now lower. So going back to the original sheet, here we're going to say no change in investment amounts from rate of return being 8%. So now the question is, what will it take for the investment amounts to change? What do you think? So I should make this number lower than the Atlantic Oil's rate of return? I think you're probably right. Let's see, how about try 0.07? That's lower than 0.073. And what happened? So you could see the difference. Now we invest nothing in the Pacific Oil and $50,000 in the Atlantic Oil. And if we try a number slightly higher than 0.073, then let's see what happens. So we could see then it's back to the original investment amounts. So from all this, we could say that the Pacific Oil's rate of return will have to be lower than 0.073 in order for the recommendation to change. So that's what we'll put down here in the original sheet. Pacific Oil's rate of return will have to be lower than 7.3%, which was the Atlantic Oil's rate of return, for the investment amounts to change. Now the third question, suppose the total amount to invest is 200,000 instead of 100,000. So you have twice the money as before. Then what happens? In addition to changing the right-hand side value of the first constraint, what other right-hand side values should be changed for the model to make sense? Okay, again, we have a copy of the sheet. So if there's 200,000, then the total amount to invest should be now 200,000. Now here it says the limit on the oil industry is 50,000. Now this 50,000 was 50% of the original amount. So now that we have the new amount, 200,000, we should change this to 50% of the new amount. Otherwise, this limit will be too low. So here I would change it to 100,000. Same thing here, 100,000. And now this one, let's see, this one came from G greater than or equal to 0.25 times M plus H. So this doesn't really need to be changed. It just says G must receive at least 25% of the amounts that go to the steel industry. So that one is okay. And this one came from Pacific Oil, less than or equal to 60% of the amounts that go into the oil companies, and that doesn't need to be changed. So from having more money to invest, we would change these three right-hand sides. So here we will put down 200,000, and here now it'll be 100,000, 100,000. And here let's make a copy of this so we could compare. So this was the original amounts. Now we'll solve the new problem with the $200,000 to invest. What do you think will happen? Probably the new amounts will be proportional to the old amounts. So probably all the investment amounts will be twice as much as the original amounts. That was what happened. So here the answer was that the second and the third right-hand side values should be changed to 50,000, and this results in all the investment amounts being twice as large as before. Speaking of the investment amounts being proportional, let's look at the fourth question. Now, what if we use different decision variables? What if we let the decision variables be the proportions invested instead of the dollar amounts? We could formulate the model that way, and we should reach the same decision. So let's try defining our variables this way. Let A be the proportion invested in Atlantic oil, P, same, invested in Pacific oil, M, H, G, similar definitions. Proportion means a fraction. So if we have $100,000 and we invest $20,000 in Atlantic oil, that means 20% of the 100,000. So it's 0.2. So then A would be 0.2. Similarly, proportion invested in Pacific oil is 30,000 divided by 100,000, and that's 0.3 or 30%. So those fractions or the percentages are what we are trying to get here. So going to the linear programming model, what it changes that the objective function will, remain the same. A would now represent the proportion. Now the objective function will be the rate of return as opposed to the dollar return. So this will be now the rate of return. And the first constraint, the first constraint, the sum of the variables have to be equal to, it's not 100,000, but it's just 1, because the proportions have to add up to 100%. A plus P should be at most 50,000 out of 100,000, which is 50%. So no more than 50%. And steel industry, no more than 50%. And these will remain the same. So now we just need to change the right-hand sides here. Then run solver to get the solution in terms of the new decision variables. Okay, there it is. So these do correspond to the solutions we had before. Before we had 20,000, 30,000, 0, 40,000, and 10,000. So these numbers are now expressed in terms of the proportions rather than the dollar amounts. Your Excel file has the solver results for all the examples we formulated, so you could use those as a reference as you do your homework. Let me also give you a quick tour. Here's a second example we formulated, electronic communications. You could see here is a linear programming model. Here we want to maximize the profit. So here you could see the coefficients or the unit profits. And here you could see the sum product function for the total profit. And here you could see the sum product function for the left-hand sides of the constraints. And the right-hand sides are here. The third example looks like this. Remember here, the decision variables represented numbers of ads to purchase on these different TV shows. And the objective was to minimize the total cost. And here was So the coefficients here were the unit cost, that is cost per ad, and it was actually in thousands of dollars. So 475,000, 340,000, and so forth. So here we got the objective coefficients, and here's the total cost we want to minimize. Now the constraints look like this. For each demographic group, you wanted the actual exposures to be greater than or equal to the minimum required exposures. So 6520, 6520 in millions were the minimum required exposures. And you could see the constraints here. Here were the minimum requirements, and here are the actual exposures we end up with. Here, notice we have a column called surplus instead of slack. Remember when we had the less than or equal to type constraints? Then we had the slack. So then slack was right-hand side minus the left-hand side. Now when we have greater than or equal to type constraints, the counterpart of the slack is a surplus. Now surplus is the opposite. It's left-hand side minus the right-hand side, because the left-hand side could be greater than the right-hand side. So here, for instance, actual exposures are 65.7 and the required was 65. So we would say that the exposures have to be at least 65 but could be more. And it turns out that in this group you end up reaching more than the required. Well, how many more? It's 0.7, and that is a surplus. 0.7, of course, means 0.7 in millions, so it's actually, 700,000 is the surplus of the young men that were reached. Now, let's take a look at solver. For demonstration, I'm going to actually redo the solver parameters here. So I'm going to reset all. The objective cell is the total cost. We want to minimize the total cost, so we got to remember to check off the min button. And the variable cells are over here, and the constraints are here. All the constraints are of the same type, so I'll do them all at once. Greater than or equal to the right-hand sides, and OK. And this part is checked off. This should be simplex LP. Now we solve. So solver found a solution, so that's good news. So let's say OK. So here's a solution. Now, do you see anything funny about this? The ads purchased must be 5.417 on American Idol, 5.417 on 60 Minutes, and nothing on the others. Now, can you actually purchase 5.417 ads? Can you tell someone, okay, I want to buy from you 5.417 ads? Well, you can't. So these numbers don't really make sense because you cannot buy a fractional part of an ad. You need integer values for the solution. Okay, well, what if I just round the values? So 5.417, so rounding it will give us 5, and this also will give us 5. Okay, so how about that? So the total cost is now $29.85. Now, does it satisfy all the constraints? Nope. In Men 1849, required exposures is 65, and we're reaching only 60. So you can see you got a negative surplus. And then here too, 60, but you need at least 65. So these two constraints are not met with this rounded solution. Okay, well, any other brilliant idea? Or how about round up one of these numbers? It was 5.4 before. Maybe make this one 6. See if that one works. Okay, now total cost is, well, much higher, as we expected. But let's see if the constraints are met. Yes, the constraints are met. Okay, so let's write that down. With American Idol getting 6 ads and 60 Minutes getting 5 ads, the total cost is $34.60. Now, is this the best possible? Maybe we could try the other way. Maybe we could try it the other way around. How about 5 and then 6? That gives us lower total cost, but then there's third constraint is not met, so that's not going to work. So then is the optimal solution 6 and 5? 6 and 5. Well, not necessarily. There might be some other integer solutions that give us lower total cost. There is a special optimization method for handling the integer programming models where the decision variables have to be integers. And we could tell solver to use that special method. So what it'll do is it'll look at all the possible integer solutions and choose the best one. For us, all we have to do is go back to solver and add a constraint that says all these values have to be integers. So we just go to add and then select all the variables. And then here, what do you think we should choose? int? That sounds like integer, right? So click on int. That gives us integer on the right hand side. And okay, so this additional constraint will force all the variable values to be integers. Let's click on solve. Found the integer solution. Say okay. There it is, 50053. Now, which was a result you saw already originally, 3300. So here, the actual solution is to buy 5 ads on American Idol, 5 ads on 60 Minutes, and 3 ads on Law and Order. The total cost from this is 3,300. That's in thousands of dollars. You could see this solution gives us lower total cost than the one we tried before.